Hey there, physics friends. We are going to talk about the damped harmonic oscillator, and specifically we're going to focus on a case called weak damping, in which the system still oscillates back and forth, losing a little bit of energy each cycle, but you still see oscillations. Just so we're clear, you can imagine a system like the following. Let me get the black pen here. We have, if you like, the mass on a spring. We still have this displacement from equilibrium, quantifying the system's coordinate. But now let's consider more than one force on the system. Let's say we have a spring force, but then we can also have a drag force. And that drag force is going to be, in this case, proportional to the velocity and pointing in the opposite direction of the velocity. So if in the absence of drag, we can remind ourselves what the equation of motion looks like. Second derivative of x, or m times the second derivative of x, plus kx is 0. And we've alternatively expressed this as x double dot plus omega naught squared x is equal to 0. And omega naught squared here, or omega naught rather, is square root of k over m. That's the resonant frequency of the system without drag. But if you have drag, then we have another force in the system. In addition to the spring force. And that additional force is B times V, where we'll write V as x dot. We can re-express this as the following: x double dot plus 2 beta x dot plus omega naught squared x is equal to 0. And here we've defined this term beta to be the drag coefficient B divided by 2m. Okay, and as we've seen, a solution for this equation of motion is given by the following, where we have an exponential decay term multiplying a series of exponentials. Now, we're going to consider something called weak damping. And weak damping simply means that beta is less than omega naught. And the implication for why the relative size of beta, what is the importance of the relative size of beta and omega naught? Well, if beta is bigger than omega naught, then this quantity up here is a real quantity. If beta is smaller than omega naught, then this is an imaginary quantity. We have the square root of a negative quantity. So we're going to consider weak damping, in which the argument of the square root is negative, so we'll have a complex exponential, and we'll see that that leads to oscillations with a decay envelope. Specifically, we can write this term square root of beta squared minus omega naught squared as square root of minus omega naught squared minus beta squared. Now the term in parentheses is positive. Square root of minus 1 is I, and then inside the square root we have a positive quantity. So this square root term is real, and it's multiplying an imaginary term. So we're going to have these complex exponentials in our position versus time expression. Rather than writing out this square root every time, we're going to define a new term called omega 1, where omega 1 is defined to be the square root of omega naught squared minus beta squared, and that's the new oscillation frequency given the presence of damping. Okay, and what we can see is if there's a little bit of damping, then omega 1 will be close to omega naught, and in the limit that beta goes to 0, meaning there's no damping, then omega 1 is exactly equal to omega naught. So here we have the expression for weak damping. We have C1 times a complex exponential plus C2 times another complex exponential. This whole term in brackets is simple harmonic motion with angular frequency omega 1. And then outside we have this exponential decay. Okay, and when you plot this all out, you get something that looks like the following. You have this exponential decay envelope, inside of which you have these oscillations. So let me call this exponential decay. I'll write that in blue, that's the blue envelope. And then the simple harmonic motion is the oscillation. And I guess the product of the two gives me the red curve. Okay. Cool. And this, of course, is a plot of position as a function of time, displacement from equilibrium as a function of time. Now, this function in weak damping is not exactly periodic, right? It's a periodic function multiplied by exponential decay. So what does it really mean to talk about the period of this function? Well, one way to quantify the period is to say that it's the time in between successive maxima, and we could call that the period t1, between successive maxima of the function. So how is t1 related to omega 1, say? What we're going to show is that this period t1 is given by 2 pi over omega 1, which seems sensible that the period is 2 pi over the angular frequency, but we actually want to prove that that's the case given this expression for x of t. So let's dive into that. We'll start by re-expressing x of t in a different form. Instead of the complex exponentials, we can use the definition a times the cosine of omega 1t minus a phase. And we know from simple harmonic motion that those are equivalent expressions. The term in square brackets here, the complex exponentials, is equivalent to writing a cosine omega t minus delta. And here we want to find the times for which this function is maximized, right? The local maxima. And for that, we want to take a derivative of this function with respect to time and set it equal to 0. So we want to look at x dot of t, which is going to have two pieces. It's going to have a derivative of the exponential times the cosine plus the exponential times the derivative of the cosine. And in both of those cases, you're going to get the exponential, okay? And when you take the derivative of the exponential, you get a minus b, and then you leave the second function alone. And then when you leave the exponential alone and you take the derivative of the cosine, you'll get minus omega 1a times the sine of that function. And so we have this. And we need x dot to be 0. That happens when the argument inside equates to 0. Now that happens when the tangent of the argument omega 1t minus delta is equal to minus beta over omega 1. Now the tangent function is periodic with a period of pi. That means every time the argument of tangent grows by pi, tangents is going to repeat. So this condition will be satisfied every time the argument grows by pi. Another way to say that is if you wait a time pi over omega 1, then this omega 1 times t term equals pi. And every time you wait this amount of time, this tangent function repeats. Okay, so we can tell then that the spacing between zeros, the spacing between extrema values of x of t are spaced by pi over omega 1. But we don't just care about the spacing between extrema, because the first extrema is a max, the next one's a min. We want the spacing between maxima. So the spacing between maxima will be twice this, 2 pi over omega 1. And that's exactly what we set out to show, is that this spacing will be equal to 2 pi over omega 1. So now we have a way to talk about the time between extrema of a decaying exponential. It's 2 pi over omega 1, where omega 1 is related to the resonant undamped frequency omega naught, and it depends on how much damping there is. The more damping there is, the smaller omega 1 is, and in the limit where the damping goes to 0, You just have the resonant frequency with no decay envelope. Good. Well, hopefully this gave you a little sense of damping, and in the case of weak damping, which is an extension of simple harmonic motion. That's all for today, but until next time, take care and be well.